On this video, we will introduce the idea of a sequence. So let's start by looking at this introduction example here, which states the following. It's an example of a sequence. And let's take a look at the sequence and see if it follows a pattern. So here we have what we call a sequence, which is just a list of numbers. And notice that in the first number, we have a 3. The second number in the list is 5. The third is 7. And the fourth is 9. Now, each of those numbers are what we call a term. So here in the sequence, we're only seeing 4 terms on the sequence. Now, does this sequence seems to have a pattern? Well, notice that in order to go from 3 to 5, we needed to add a 2. But notice that in order to go from 5 to 7, we also added 2. And from 7 to 9, we also added 2. So notice that once we know kind of like the pattern of the sequence, then we can start guessing what's the next number. Because if I know that from the first to the second, I added a 2, and from the second to the third, I added a 2, then obviously to go from the fourth to the next term, we needed to add a 2. So perhaps we can guess that the next number in the sequence is 11. And perhaps the next number, since start seeing a pattern, perhaps the next number is 11 plus 2, which is 13, and so forward. So we can say that now, at least the pattern, that's an n, the pattern of the sequence is we got the previous term, and we added a value of 2. Because notice that if we get 3 and we add 2, we get the next one. So in order to get 5, it was the previous term plus 2. In order to get 9, it was the previous term plus 2. So this seems to be the pattern. We look at a term, we add a 2, we get the next one. So now that we have identified a pattern, so the question now becomes, is it possible for us to write down a formula which we can use to find the terms of the sequence? And for this is our main idea for today. The main idea for today is to properly write down some kind of formulas which we can use to start finding terms in the sequence. So at least for this question, we're going to come back to it at the end of this lesson, and we're going to try to answer it. But this is going to be our main objective for today. Our main objective for today is to start analyzing sequences, taking a look at the pattern of those sequences, and use those patterns to start writing down formulas to properly define that sequence. So we'll come back to this question at the end of this video. But before we go into the idea of writing down formulas for sequence, let's just review some definitions of what we're going to be discussing today. So the way that we're going to be defining a sequence is just going to be a list of numbers, or sometimes referred to as objects, and that's it. It's just a list of numbers. So here notice that we have it a list. It's 3, 5, 7, 9. Now, when we talk about sequence, they don't necessarily have to follow an order. So as long as you have a list of numbers or objects, we can define that as a sequence. Now, a finite sequence is a sequence. Well, I'm sorry, before we define finite sequence, let's just give an example of a sequence, which, I don't know, we can do the one that we did in the introduction. So this is a sequence. It's a list of numbers. Here's another example. And so forward. It's just a list of numbers. They don't necessarily have to follow an order. Now, there's two types of sequences that we're going to be discussing: finite sequence and infinite sequence. So a finite sequence it's a sequence with a finite number of terms. Which in this case, notice that the sequence right here, it has 1, 2, 3, 4 terms, 1, 2, 3, 4, 5 terms. So here's an example of a finite sequence. So it can be the same one as we did. Here we can say that there are 4 terms, finite. There's a finite number, that's 4. Here's another example. Let's make it something big. 70. Now, notice that here I'm doing dot, 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 dot. This is just saying that there's just a lot of terms here. There's just a lot of terms, which I'm not going to list it, but I'm going to give you the last one. So here, notice that if we can see that the pattern is 1, then we can say that this sequence right here has 70 terms. So it is a finite number of terms. Like you can actually count them and give a numerical value to how many terms there are in a sequence. Now, an infinite sequence is, well, a sequence with infinite set of terms. Here's an example. What we were given on the introduction question, that was an infinite sequence. Because notice that here, I'm only listing 3, 5, 7, 9, and I'm saying here's exactly 4 terms. But the moment that I start doing dot, 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 I'm just saying that this is just going to continue infinitely. Notice that I'm not putting a number on the right hand side after the dot, because that is just implying that there's just a lot of terms after that, and we cannot count them. There's just infinite amount of them. Here's another example. I don't know, 7, 9, 21, dot, 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 30, comma, dot, 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 dot. And notice that here, I'm just saying, well, I mean, I'm not going to list the terms between 21 and 30, but then I know that after 30, there's just a lot of them. So notice that these are just examples of infinite sequences. It's just sequences that doesn't have a ending term. Finite sequence are just sequences that you can actually define them. Look, we have 70 terms here. We have 4 terms here. And a sequence is just a list of numbers or objects. Now let's go and start discussing what we call the formulas of the sequence. And we mostly use the formulas, and we're going to talk about 2 types of formulas, to answer these questions. So how can I find terms in a sequence? And the main idea for today is to define those 2 ways that we can define sequence. So there are 2 ways to define a sequence, either by what we call the explicit formula or either by what we call the recursive formula. And we're going to give one example of each. So here we have an example of what we refer to as the explicit formula. And we're going to see why it's called the explicit formula. But before we start discussing the explicit formula, we have to understand some notation for the explicit formula. Because the explicit formula has this weird notation here, where A, it just means the term. When we call A subscript n, this means the nth term. If n is 7, then we're going to talk about the 7th term. So if we go back to perhaps the example that we had here on the introduction question, in this infinite sequence, 3 was the first term. So we can refer to as 3 as A subscript 1. 5 was the second term. So I can refer to as 5 as A subscript 2, saying that this is the second term. 7 was the third term, so therefore I can refer to it as A subscript 3, A subscript 4, and A sub n, it just means the nth term. We haven't defined it, but we're just talking about some finite term. So A little n is going to be referred to as the nth term, and n, it just refers to a value. So A of n is the nth term, and n is just a value that we use to define a term. So let's just keep those ideas in mind and let's actually use them, because I feel like for these examples it's better to just use them instead of just writing them explicitly. So let's take a look at the explicit formula method. So we can use the explicit formula to define a specific terms. So in this example one, it says find the first four terms of the given sequence. This formula that we do have here, it's a formula that we use to define a term. And how can we find the members of that sequence? Or how can we define the terms of that sequence? Well, we're going to be assigning values for n. So if I want to know under the explicit formula, if I want to know what's the value of my first term, well, that's going to be given to me whenever I substitute the value n equals 1. Because notice what's going to happen. If we allow n to be equals 1, then we have a of 1, which this is saying that whatever the value that comes out of this is going to be the first term. And now we're going to have 3 times. But notice that here I'm letting n equals to 1, so I'm just going to substitute it. Now it becomes 3 minus 2, which is 1. So what this is saying is that the first term in my sequence is 1. If I want to know the second term in the sequence, I'm just going to let n be equals to 2. And let's define what that is. Well, a subscript of n, but right now I'm letting n be equal to 2. So I have a subscript of 2. And note that this is the notation that we use for the second term. So the second term is going to be defined as 3 times n, but n, right now we're letting n be equal to 2. Minus 2, so that becomes 6 minus 2, which is just 4. So what we're saying here is that the second term on this sequence has a value of 4. And if we continue doing this, let's define the fourth term. So if I want to know what's the value of the third term, I'm just going to let n be equals to 3. So we're going to have a subscript of n. So notice that all I'm doing, I'm just plugging n to those 2 spaces there. 3 times 3 minus 2. So now that's 9 minus 2, which is just 7. So what we're saying is that the third term has a value of 7. And lastly, let's just, since we're asking for the first 4 terms, so n equals to 4. Let's see what happens when n is equals to 4. So we're going to get 3 times 4 minus 2, which is 12 minus 2, which is just 10. So what we're saying is that the fourth term on this sequence is 10. So far, what we have done is we have found the first 4 terms of this sequence. So if we're going to start picturing our sequence, my sequence was going to have a first term of 1, and a second term of 4, and a third term of 7, and a fourth term of 10. And notice that this is an example of an infinite sequence because we can define any value of n. There is no restriction on n, so we can just define it as this. So we just get a little picture of what the sequence is. And the reason why this kind of formula is called the explicit formula, it's because you can explicitly find the value of the sequence. Find the value of the term in the sequence. So let's assume that you want to find the 30th term on the sequence. So if you want to find the 30th term of the sequence, you explicitly have to just substitute n equals 30th. So let's find that out. So a of 30th, that's going to be 3 times 30 minus 2. So that was going to be 90 minus 2, which is just going to be 88. So we know that the 30th term in the sequence is defined as 88. So perhaps you have first, fourth, third, fourth. There's a bunch of terms. So here we have the 5th, the 6th, the 7th, blah, blah, all the way to 29. And once you reach 29, you're going to have the 30th term, and you're still going to continue going. So notice that the reason why this is called the explicit formula is because you can explicitly define the terms in the sequence. If you're looking for the 100th term in the sequence, you're just going to have to define, or you're just going to have to plug in n to be 100. If you want the 1,000th term in the sequence, you just got to plug in n to be 1,000. So that's the reason why we call it the explicit formula, because you can explicitly find the terms in the sequence. Now, The same way that we can also define sequences are by the recursive formula sequence. And notice that the recursive formula, it just has, the notation is not as clean as the explicit formula. So before we go into the actual examples, let's just review some of the notation. So again, sometimes we use S of A of n or A of k, like it doesn't really matter. It's just A, it's just standard. So A just means the term. Sometimes we can use a little n, sometimes we can use a little k, or we call it subscript, to just define the nth term, just like we did explicitly, or the k term, depending on what subscript you're using. Now, notice that when we talk about the recursive formula, we also have a either n minus 1 or a either k minus 1. So this just means the n minus 1th term or the previous term. Let's just picture what this is. So if let me just give you a very fast. So here we have a sequence. So let's define, this is my third term. So I can define as a subscript 3. This is my second term. So I can perhaps define this as a 3 minus 1, which is just a of 2, which is, if I'm looking at 3, let's assume that you're standing at 3. My previous term was 2. The way that I can define the subscript for that is just forward minus 1. If I want to find the first term, I can define it as just perhaps a 2 minus 1. So if I'm standing at 2, the previous term is the first one, so I can just define it as where you're standing minus 1. So a 2 minus 1, which is just a of 1, aka the previous term. So, but still, a of k is the term, a k minus 1 is the previous term, and sometimes we even use a k plus 1 or n plus 1, which just means the forward term. So one way to just visualize this is, let's assume that you are sitting on a term, a of n. So this is the present. Well, the one that came before that is a n minus 1, or the past. And the one that's going to go after that one is n plus 1. So this is what we call the future. This is just notation. And it's just very important for you to understand what we mean by n minus 1, n, and n plus 1. Because we're going to use that on the recursive formula. So now that we have kind of introduced this notation, let's actually use the recursive formula. So our objective is still kind of the same. So write the first 5 terms of the sequence. So now notice that my first term, it's already given to me. My first term is a value of 3. Now, how can I find the second term? Well, if I want to find the second term, I need to let k be equals to 2. If I let k be equals to 2, then I'm gonna have a subscript of 2, which is exactly what I need for the second term. And now notice what's gonna happen, because now if I let k equals to 2, now this a is gonna be 2 minus 1, which is just 1, and then plus 1. But understand what this means. This means the first term. So now notice that we're defining the second term in terms of the one that came before, which is the first term. So I can just plug in what I know. So the second term is going to be 2 times the first term, which we already know what the first term is. The first term is 3 plus 1. So now I can say that the second term is equivalent to 6 plus 1, which is just 7. So my second term is just 7. Let's define the third term. So if I want to know the value of the third term in the sequence, I need to let k be equals to 3. And if I let k be equals to 3, let me just plug that in on my recursive formula. So I'm going to have a of 3 equals 2 times a k minus 1. But if right now my k is 3, then that's going to be a subscript of 2. So a of 2 plus 1. But notice that we know what a of 2 is. We just found it previously. The second term has a value of 7. So therefore, the third term is 2 times 7 plus 1, which this is equivalent to just 15. So therefore, my third term has a value of 15. Let's define the fourth term. So even though here it says find the first 5 terms, let's just do the fourth term up to the fourth term because of the space that we have left. So let's define the fourth term. So k equals 4. So we're going to let a of 4 equals 2 times a 4 minus 1, which is just going to be 3, plus 1. So now a of 4 is 2. The third term was 15 plus 1. So this is 30 plus 1, which is just 31. So therefore, my fourth term is 31. Now let's just picture what we have found. Let's just picture what we have found here. Let me just erase all this. What we have found is that we have defined a sequence. We have defined a sequence. Because now our sequence, and again, we're not looking at B right now. Right now, my sequence, it kind of has this form. If it has the first term is defined as 3, the second term is defined as 7, the third term is defined as 15, and the fourth term is defined as 31. And there's just going to be infinite amount of terms, so you're just going to do that. And notice that the sequence, the results that we have in the sequence, it does follow what my explicit formula was saying, because this is what we refer to as the explicit formula part. So the explicit formula is saying, look, for you to define a term, you're going to get the previous term multiplied by 2 and then add a 1 to it. Well, let's see that is true. In order for me to define 7, I'm going to get 3 times 2, which is 6, plus 1, that's 7. 7 times 2, that's 14, plus 1, that's 15. That's what we're saying here. 15 times 2 plus 1, that's 31, and so forward. So notice that the sequence does follow the form. It does follow what the explicit or the recursive formula was saying. Well, let's talk about now some of the advantage and disadvantages of these two ways to define sequences. Now, coming back to the explicit formula, it's preferable for you to use the explicit formula because it's just easier for us to define terms in the sequence. So let's assume that you want to just find the 99th term. So all you gotta do is just plug in n to have a value of 99 and plug it in and you're done. Under the recursive formula, note that in order for me to define a term, I need to know the one that came before that. And I need to know the one that came before that. And the one that came before that. So right now, for me to know the fourth term, I need to know the third term. But in order for me to know the third term, I need to know the second term. And for me to know the second term, I need to know the first term. So notice that if I want to find the 99th term, I needed to already define the 98th term. And to define the 98th, I needed to define the 99th term. And if I want to define the 99, I need the one that came before that. So it's just faster for us to start using the explicit formula instead of the recursive formula. And this is not to say that the recursive formula it's not important, but it just in the context of just finding members or finding terms in the sequence, we usually just use the explicit formula because it just gets those to the objective faster. And this is actually a limitation. So this is actually a limitation that the recursive formula has that the explicit formula does not. So for the recursive, A big limitation the recursive formula had is that you need to know the previous term to define a term. In this case, if I want to know the 99, I need to know what the 98 is. If I want to know what the 98 term is, I need to know what the 97 term is, and so forward. Where this is something that the explicit formula doesn't have. So the big limitation about the recursive formula is that we need to know all the previous terms that came before a term that you're looking for. So that's just going to require a lot of work. The last little point that I want to, this doesn't refer too much to sequences, but we will use these expressions throughout our studies of sequences, and that's the idea of a factorial. So just recall what a factorial means. Factorial, we usually use the exclamation point to indicate factorial. And what this factorial is saying is you're going to multiply by descending with the value of 1. So therefore, if I want to find the fourth factorial, I'm going to get the fourth term, and I'm going to multiply by a number that is lower than 1. So 4 minus 1 is 3, minus 1 is 2, minus 1 is 1. But notice that we just stop at 1. Because what would have happened if we would have defined it 4 factorial as 4 times 3 times 2 times 1 times 0? By introducing the multiplication of 0, all we're doing is making everything be equal to 0. Because this is just going to be a big number. I mean, we already know what's 24. And 24 times 0 is 0. So if we were to define factorials as to multiply by a decreasing of 1 up to 0, then our result was it's always going to be 0. So that way we always stop at 1 when it comes to factorial. So the way that we define factorials is just you get your number and then you multiply by minus 1. So 4 minus 1 is 3. And then you multiply by the number who comes after minus 1, which is 2. And minus 1 is 1. And this is just how we define factorials. Now, that's a simple idea. Just you keep multiplying by a decreasing of 1. But sometimes we do have expressions. And there are different ways to think about this kind of expression. So let's just introduce 2 quick examples for simplifying factorials. So the way that we are going to define this is if we want to simplify expressions that deal with factorials, well, let's understand what this is saying. This is saying that 8 factorial is 8 times 7 times 6 times 4 times 3 times 2 times 1 over 2 factorial is 2 times 1, and 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. If we want to do it the long way, we would multiply all this, we would get a number, we would multiply all this, and then we would multiply it times 2, and that would be our denominator. That's a lot of work. But notice that 8 factorial, I know that I can write as 8 times 7 times 6 times 5, 4, 3, 2, 1. At least this is how we define factorials. But now, notice that up to this expression right here, 6 times 5 times 4 times 3 times 2 times 1, this is equivalent to 6 factorial. So now, perhaps I can just rewrite 8 factorial as 8 times 7 times 6 factorial. And if I define it as 6 factorial, notice that the 6 factorial, they're all multiplying. So they're all multiplying. Therefore, the 6 factorial can cancel out with this other 6 factorial. And now, my whole expression just becomes 8 times 7 over 2 factorial, which is just 2 times 1. And now we just define these values. So that will be 196 over 2, which is just 98. And now we can use that same idea to to simplify expressions that perhaps they have, they're not defined by numbers, but defined all by variables. Because now n factorial, by definition, I'm going to get n, and then I'm going to multiply by n minus 1, and then I'm going to multiply by n minus 2, and then I'm going to multiply by n minus 3, and then I'm going to keep doing it until I reach a number of 1. So this is at least how this is being defined. So n minus 1 times n minus 2 times n minus 3, and so forward until I reach a number of 1. But now notice that no, this is just, it just seems to have a lot of problems in here. Well, perhaps instead of defining n factorial, it is possible for us to define n factorial in terms of the n minus 1 factorial. Because now notice that this expression right here, n minus 1 times n minus 2 times n minus 3 times 1, or all the way up to 1, this is equivalent to just n minus 1 factorial. So notice that we start at n minus 1, and then we multiply by a decreasing of 1. So perhaps the value of n factorial, I could just rewrite as n times n minus 1 factorial over n minus 1 factorial. And I notice that the n minus 1 factorials are going to cancel out. And now that just becomes n. So I hope that this lesson was helpful. And again, this idea or this lesson was just to refresh your idea when it comes to sequences and a little bit of factorial at the end.